director of OSRC. I'm also the project scientist of Wallaby, which is one of the surveys on a radio telescope. And today I have been tasked to give a 30-minute presentation on all of radio astrophysics. Obviously, it's a huge topic, and I will do my best, but a lot of these things I'll be presenting could take have their own full day or at least a week for some of them to explain properly. I'll also note there is a QR code that you can scan just for a link to a survey that that Natasha has prepared. Just we'll have it in all our slides, so it's okay if you don't have it right now. So to begin, I would first like to acknowledge the traditional custodians on the various lands on which we are meeting on today and pay my respect to their elders past and present. I'm currently on Whadjuk Noongar Boodja, so that's the people of the Whadjuk region. And I'd also like to extend this respect to any other Aboriginal or Torres Strait Islanders who might be present today. I'll note that the traditional custodians were the first astronomers, and I thank them for sharing their land and their sky and their stars with us. And here on this right-hand side here, you can see this from Stellarium, and this is the Kamilaroi view of the emu in the sky. And so those in the southern hemisphere see the Milky Way, and we see this amazing emu, which allows the Kamilaroi people to know when to go hunting for eggs or when the emus are running around. And so starting with the standard diagram that most of you probably already know. So we're looking at different aspects of astronomy, and when we look at it, it depends on where we are and what we can see, right? And so I know a lot of you are probably using a lot of different telescopes, and today we're here to talk about radio telescopes and what we can observe with radio waves. And so that's this part of the electromagnetic spectrum where we can see it's completely clear through the atmosphere. And so we're lucky that we can have ground-based telescopes that allow us to see all different parts of the radio domain, and we can see different features. And I will note that I will interchange mostly between frequency and wavelength, probably mostly speaking about frequency. And so just to remind everyone the conversion between frequency and wavelength. And so a few millimeters, so about 3 millimeters, about 100 gigahertz. And when we go up to about 30 meters, that's around 10 megahertz, just using that standard conversion equation shown on the screen right now. And so where did it all begin? Well, radio astronomy started when Carl Jansky discovered the first astronomical source in the early 1930s. And so that's why one of our big units is named after him. And so here you can see he's working on this directional radio antenna. And he was actually hired by the telephone company Bell to try to figure out some of the static that they were hearing. And when he was tracking the static, he noticed that there was it was pretty strong every 24 hours. And so he's like, oh, it must be something to do with the sun or whatnot. But then he realized it didn't coincide with the sun. It was actually really strong every 23 hours and 56 minutes, which is also the sidereal day. And so he referred to one of his colleagues who is an astrophysicist and mentioned that it's probably an astronomical object in the sky. And so with further investigation, Jansky realized that he was detecting the signal from the center of our galaxy, the Milky Way. And so that was in the 1930s, and now we have this image from Meerkat, and so almost 100 years later, we're getting these amazing images of that galactic center, that feature that Jansky detected way back when. Obviously, this image is much more high resolution. You can see not only the galactic center with Sagittarius A star and around it, but you can also see these magnetic filaments. And so where do all these radio features and radio detections come from? Well, there's different mechanisms that actually can emit radio waves. And so one of the big ones that a lot of people know about, but I'll review here, is synchrotron radiation. And so synchrotron radiation is when charged particles, usually electrons, are traveling really fast, so close to the speed of light, so relativistic speeds, and they're traveling around or near magnetic field lines. And so you can see in this diagram here, there's these straight magnetic field lines, and these particles, mostly electrons, are spinning around. And this spinning motion, when they're doing the spiral, there's actually an acceleration in one direction as they're moving around. And so this changing of motion emits a photon. And those photons are emitted with different frequencies based on this equation here. So every electron, we can see what the frequency is emitted, and all that comes out as broadband or continuous emission, as we call it. And so in radio astronomy, we can see this broadband or continuum emission in different sources. And so I'll go through a few of the sources that that we can detect in synchrotron. And so here are some images of supernova remnants. And so this is actually the same Meerkat data, but it's a little bit shifted over, and we can see this nice supernova remnant. And so this is done with the Meerkat telescope and radio. You can see the nice the shell feature, but referring it to other wavelengths, if we're looking at supernova remnants, obviously you can see them in other wavelengths as well. And so here there are two images on the top two panels here from X-ray telescopes, and then we have one from the ACA telescope. Oh, and all these telescopes, don't worry if you don't know them all. Laura is going to talk about them, so I'm just going to put them out there. But yeah, she'll tell you which telescope is what and what they do. But anyway, so we have X-ray and we have radio. And you can see if you put all those images together, we have different features that we can see. And so we see the X-ray features, but we also see the radio ones. And so it's different structures. And we can see this shell-like feature here from the supernova remnant. And so combining this, we actually see a lot more and get a lot more science out of it. Other things that can be detected are referred to commonly as radio galaxies, and that's a whole classification of objects that basically are AGNs that have this relativistic jet and possibly radio lobes. And so here is that standard schematic of an AGN that most of us are familiar with, and depending on where the observer, where they see it, they see different things, right? And so different types of AGN. But in general, we can see in radio, we can see several features from the AGN. So we can see the galaxy and these jets, so these thin relativistic jets that's coming out of it, and then these large radio lobes. And so this image here on the top is a composition between optical and radio. And so when we look at the two panels below, we can see what we can see in optical and what we can see in radio. And so there's a lot of stuff that we can see in the radio that you can't see in the optical, and vice versa, right? And so working together, we get this nice image where we can see these nice broad radio lobes that expand a very large extent beyond the actual disk of the galaxy, which is centered right in here. Other things that emit synchrotron emission are galaxy clusters. And so here is an image of the Abell cluster. And so we can see the X-ray, the high energy X-ray from the cluster medium. And there are actually these red splotches here are radio emission. And so these are actually taken from the GMRT telescope and zoomed in on one, and we can see that it's these shock-like features. And so we have this bow-like shape here, and that actually emits synchrotron radiation that can be detected in radio. And so we've detected a whole bunch of radio sources, and so what do we do with it? Well, one of the things that's commonly done is measuring the spectral index. And so here we see, synchrotron emission generally follows, has a power law spectrum here, which I show right here, sorry. And so it's the relationship between the flux and the frequency. And so a single one for an individual electron or one of those relativistic particles, you can see has this kind of power law decay. And to get the curve, if you add up if you sum up all individual electrons together, we get this curve here. And then we have this nice decreasing slope right on here. And so that's this is the flux compared to the frequency, and so we can see that it's proportional to the flux. So the flux is proportional to the frequency to a certain power, and that power variable is the spectral index. And so reviewing just those objects that I referred to that have that emit synchrotron radiation, here we can see the typical spectral index for these objects, and they're also ordered based on size. And so the smaller objects here up to those galaxy clusters, and you can see different spectral indices for all these objects. Radio galaxies, since there's multiple parts, they have drastically different things. The galaxy in the center has a different spectral index than the radio lobes that are far out from the actual galaxy. Other things that involve magnetic fields is polarization. And so we have polarized emission, and that shows us the magnetic field lines, or we can get magnetic fields, and we know the directions and strengths of those. And so you can see those in the magnetic field lines that are shown in this image here on M81. So it's superimposed. We have these magnetic field lines. And at radio frequencies, most of the polarization that is detected comes from that synchrotron process. So I know polarization can come from other mechanisms. For example, dust grains sometimes get magnetized, but most of the polarized emission at radio frequencies is from synchrotron. And so moving over to other things that emit radio waves, and sticking to the theme of magnetism, is pulsars. So pulsars are magnetized neutron stars, and they pulse, or they kind of move around, and you can see this schematic of it and this little pulse feature here. And so these were detected by Jocelyn Bell back in the 1960s, and she noticed in the data, you can see the original set of data, she noticed these little spikes in the data, and they were fairly periodic. And so she investigated those further, and that became the discovery of pulsars. And so we have these pulsars here, and they're almost like these lighthouses that moves around and it shines, and we see this the emission spikes when it's directed at the observer here. And with pulsars, some of the things that we like to measure is the dispersion, so dispersion measure. And so here we can see that pulsar. So this graph here, we have the pulse, and so that's that same pulse that I've shown you. So when that lighthouse shines towards you, we have this nice big pulse peak here. But if we break it down in frequency, we see that the frequency is actually dispersed. And so here's a video that kind of shows that. And so as the photons come out of the pulsar and come towards the observer, if they interact with other charged particles in the universe, or in the intrastellar medium, for example, protons or electrons or whatnot, you can see that the longer wavelength ones right there, longer wavelength photons, they slow down, or sorry, they get there's a dispersion in when they can actually reach the observer, right? And then we get this plot right here, which is these plots here. So it's based on the frequency. I don't know why it's doing that. I'll just pause it. There we go. And so we can see the same plot here. And so we have the frequency here, and then the time of when that pulse actually gets there based on the frequency. And so we have these nice dispersion measure plots here. And a lot of times that dispersion allows us to understand what's in between us and that pulsar, for example, right? So the lower the dispersion measure, the fewer particles, or the fewer whatever is in between us. And in theory, the higher the dispersion measure would mean that there's more particles. And so I've mentioned pulsars, which generally have dispersion measures, a few hundred parsecs per centimeter cube. But then we have these things called FRBs that I'll show you in the next slide. And FRBs, or fast radio bursts, tend to have much higher dispersion measures. And so FRBs, or fast radio bursts, sorry, right there. Fast radio bursts, are believed to be extragalactic sources. So they come from all corners of the universe. And so here is a nice video of it. And so same thing, we have these photons coming towards the observer, and as they pass through different media, the photons are dispersed, and we can see the more that passes through, the higher the dispersion is. And so as they come towards the observer, the more stuff that's passing through, and we can see that, right? And so that dispersion measure ends up being closer to like hundreds to a few hundreds to thousands of parsecs per centimeter cubes by the time it gets here. And so that's a lot more. So that's a lot more material. And so that's why we have these higher dispersion measures for these fast radio bursts. Astronomers still don't really know what causes these FRBs. They could be the very, very energetic burst of pulsars, for example, or they could be different types of stars that have magneton type magnetos that have these magnetospheres, and it's something to do with that. But they're not quite sure what the mechanism is, but we know that they're much further just because the dispersion measure is that much higher. And so FRBs have been used to probe the, for example, if there's missing matter in the universe or whatnot. All right, moving forwards. And so let's go to non-magnetic type of emission that we can detect in radio. And so we have Bressilum emission. And so this is when electrons are accelerated by electric fields, any ions and whatnot. And so the typical one that we hear about is free. So that's when free electrons are moving around. They get some energy, or they release some energy, and photons are either emitted or absorbed, and so that's free. But in that one, the electron is still free in this whole interaction. And then there's ones, so if there's free, obviously there's bound, and bound free, and vice versa and whatnot. These are less used terms, but I will get into the spectral line emission as well. But we'll just look at the free one first. And so free emission we can see in H2 regions that contain ionizing stars. So you can see here, there's this image where we have this nice bright H2 region. We have these bright H2 regions here, and then all around it, there's this radio emission. And this is generally considered free emission. And then the red, sorry, that's the blue. And then there's also some red infrared in these images here. And so this is just an example, and a lot of things happening in H2 regions, which I'll come back to when I get to spectral line stuff as well. And so now I'll move into spectral line, which is probably my comfort zone because I do spectral line a lot more. So spectral line emission is that bound state. And so when an electron is bound to a atom or a molecule, and it changes energy states. And so that's a lot of times, that's when it changes that energy state, it either emits or absorbs a photon. And that energy is equivalent to a certain frequency as per this equation down here. And so here's just a little diagram that shows, so we were talking about when we were talking about synchrotron emission, it was mostly continuum emission, broadband, like I said, it emits at all frequencies. But when we're looking at spectral line, it's discrete energy packets, and so we have very discrete peaks. And so this is an example of emission spectra, but then obviously, photons can also be absorbed by molecules or atoms, and that's where we get absorption here. And so I'll go into those into a bit more detail. And here are just a couple, a table of a lot of the rest frequencies that are commonly used in radio astronomy. So we can see all the different frequencies, and like I said, it's from few tens of megahertz up to up to 100 gigahertz or so for the radio. And so a big one that I look at a lot, which I'll explain a bit more now, is this top one here. And so that's H1, or neutral atomic hydrogen. And so neutral atomic hydrogen comes from the hydrogen atom. And so we have one proton and one electron. And sometimes their spins will be aligned, and that's a higher energy state, right? And so when the proton is facing up and electron is facing up, it's in a higher energy state. And so that electron is going to want to flip into a lower energy state and then emit a photon. And generally that photon is emitted at 21 centimeter wavelength, or 1.4 gigahertz in the frequency. And so this transition is considered to be a forbidden one because it doesn't happen on Earth, right? Getting that higher energy state, but because there's so much hydrogen in the universe, this happens commonly in the universe. And so in galaxies, this transition, or this these photons that are released, we detect them as H1 emission, so neutral atomic hydrogen emission. And so here is a data cube of H1 emission. And so each channel that is playing through here is a slice of frequency. I'll note that it does say velocity on the top, so a lot of times I switch between. There's a conversion thing, but frequency, velocity, very similar things. And so as we go through each step, each channel of frequency or velocity, you can see that there is a certain amount of H1 brightness or H1 flux, and we can plot that on this flux versus velocity or frequency graph here. And you can see that there's, and if this one, so this one is a rotating disk, and so this is an H1 disk. If it's rotating, then half the galaxy is kind of moving towards us and half the galaxy is moving away from us, right? If it's a frisbee type of thing. And so we can actually have a blue shifted side and a red shifted side. And so as the galaxy moves through velocity, we can see that. And usually that central velocity, we take as where it is in the universe and how far it's moving away from us. And so we can use the central velocity as a proxy for distance for where these sources are. A bit more into the calculations of H1. And so H1, so same spectra here that we can see. And so if we want to know the mass of the H1, so how much gas, hydrogen gas is in the galaxy, we can actually do it quite easily because in galaxies, H1 is optically thin. And so for every spin flip transition, right, that happens, we know how much that atom weighs. And so depending on how bright, how much flux comes from the galaxy, we know exactly how many H1 atoms are sitting there. And so this equation here does that, and basically we take the flux density, which is the area under this curve, and so we take the integral area, plug that in, we have the distance, and then we know how much H1 is there. Another useful thing that H1 can tell us is also the dynamical mass. And so if the galaxies are these rotating disks that I mentioned, as they're rotating, they have this Newton thing where, all the contained mass is in there, and we can actually determine how much mass is in there based on this rotation. And so a lot of times we use the dynamical mass, which is the contained mass. And this is where some of those measurements of galaxies having more dark matter or more mass come from, is that they're rotating too fast. And we can actually see that using the H1, using the rotation curves as well. Something that might be of interest is these spider diagrams, or that's a colloquial term, but they're the velocity diagrams. And so you might see these, and I'll just want to break it down just because sometimes you see them and you're not quite sure. And so when I was going through that video where you saw each slice of velocity or each slice of frequency, and that was a bit of the galaxy, well, this is, whoops, sorry. This is it in a more schematic version. And so you can see as we step through each channel, we see a different part of the galaxy. And then you squish those all together and you get this spider looking like diagram. And that shows you that's a rotating disk. And there's a couple of the geometry stuff up there so you can see that. But that basically shows you what these are. And so here are a couple of images of H1 in galaxies. And so we have those 3D cubes, but when we squish them together, we can make these things called moment maps. I think Laura has a bit more about that in her slides. And then we have a couple moment maps of, so this is a total intensity. And so that's just squishing the H1 together. And so we can see where, oops, sorry, I keep pressing the wrong button. And so we can see where the peak fluxes in these galaxies, but then we also have those velocity maps here, and those are generally moment 1 maps. So we have moment 0, jargon term, sorry. And here is I think this one's a peak intensity map of the Small Magellanic Cloud, and so different ways of visualizing the H1, but we can see it spatially as well as in that third dimension. Continuing with H1, we'll look at the absorption. And so H1 absorption is a big field as well. And so absorption happens when we have this hot continuum source a lot of times, a black body, and the light has to go through a cooler cloud of H1 or something else, but mostly H1. We can see that in absorption, and so this is an example of an absorption feature, and it's more than just one object, it's more than one peak. We can actually see some structure, and some of, like a little wing is there, a little wing as well there. And so this is an example of an absorption feature in H1. All right, moving on to molecular lines. So we can also detect molecular lines in radio. And so these happen when we have molecules, and there's all different ways that molecules will be emitting. And a lot of times it's, vibration, rotation as they move around. And here is just a spectra of some molecular lines. All right, and then there are recombination lines as well. So most of you are probably fairly familiar with recombination lines. And so here is an energy diagram, but we can see some spectra for a couple of helium, hydrogen, and carbon transitions here. And here is just some stacked radio recombination lines. Again, those fun H2 regions. H2 regions have a lot of physics and astronomy in them, and especially when you're looking at radio and other wavelengths as well. But here's some recombination lines of an H2 region. And that gets me to masers. And so masers are also found to emit in radio. And so masers stand for microwave amplification by stimulated emission of radiation. So that's a mouthful, yes, but we call them masers. And this is where there's this pumping mechanism, and then it leads to this decay. And so it has that amplification. So it's a stimulated emission because they have this pumping mechanism that actually makes it. And then as it pumps through, and then a photon is emitted. And thing is, when it happens, it's actually two photons emitted at the exact same frequency, phase, and direction. So one photon actually becomes kind of two, so it multiplies in how it emits it through this pumping mechanism. And so that's why we have this nice coherent beam of emission. And so it's almost like a laser. And so masers can be considered like space lasers. And so here is a couple of the water masers in M31 and some spectra from these as well. All right, and so I have taken you through a lot of radio astrophysics. Hopefully you learned a bit. I did go a bit fast for some of it, but we do have the full 2.5 hours today, and so feel free to ask me questions. And as we go through a lot of these concepts and a lot of the information will also be described